Hello and good morning to all of you. I hope all of you are doing well and all of you are in good health. In today's class, we will be discussing 8086 addressing modes. Before starting with the addressing modes of 8086, I want you to understand that a typical program statement in 8086 has in it two identifiable components. These components are operand and instruction. Operands are basically entities that are operated upon by the instruction. An 8086 instruction can have 0, 1 or 2 operands. Again, I'll repeat it. An 8086 instruction can have 0, 1 or 2 operands. For instruction with two operands, the first operand is the source operand and the second operator is the destination operand. Always remember, for instruction with two operands, the first operand is the source operand and the second operand is the destination operand. Now, the way of specifying data to be operated by an instruction is known as addressing modes. Again, I'll repeat it. The way of specifying data to be operated by an instruction is called as addressing mode. That is, different ways in which the source operand is denoted in an instruction. Please remember, it refers to the different ways in which the source operand is denoted in an instruction. So this is what is addressing mode. So the different ways of specifying data to be operated by an instruction is known as addressing mode, and to be very specific, the different ways in which the source operand is denoted in an instruction. Now, in other words, addressing mode refers to the different methods of addressing operands. So depending upon the data type used in the instruction and the memory addressing mode, any instruction may belong to one or more than one addressing modes. So let us try to understand it in greater detail. Now the addressing mode describes the type of operands and the way they are accessed by executing an instruction. Again, I'll repeat it. So the addressing mode describes the type of operands and the way they are accessed for executing an instruction. Now, as you know, in a typical programming construct, there can be different ways in which the statements are executed. As you know, statements can be sequentially executed, or it can be executed in iteration, or it can be executed in selection. Now, accordingly to the flow of instruction execution, the instruction execution may be categorized into, as we all know, sequential control flow instruction and control transfer instruction. So, sequential control flow instructions are the instructions which, after execution, the transfer of control takes place to the next instruction appearing immediately after it. So, this is the way how the instructions are executed in sequence one after the other. So again, I'll repeat it. So sequential control flow instructions are instructions which after execution transfers the control to the next instruction appearing immediately after the program. For example, arithmetic, logical, data transfer and process control instructions are sequential control flow instructions. Now likewise, you have control transfer instructions. The control transfer instruction, on the other hand, transfers control to some predefined address or predefined address or the address somehow specified in the instruction after their execution. For example, int, call, return, and jump instruction falls under this particular category. Now, let us try to understand the addressing modes that are there in 8086. To begin with, the first addressing mode that you have is called as immediate addressing mode. Now, in case of immediate addressing mode, the destination field is the first operand that defines the length of the data. Again, I'll repeat it. The destination field is the first operand and defines the length of the data and may be a register or a memory location. So the first operand is either a register or a memory location, but it can never be a data. Please remember, it can never be a data. So the first operand is never an immediate data. Now the second operand in such kind of addressing mode is the data itself, so appearing in the form of successive byte or bytes. So in case of immediate addressing mode, the destination field is the first operand that defines the length of the data. It may be a memory or it may be a register, but it cannot be immediate data. And the second operand is the data itself, appearing in form of successive bytes or a byte or bytes. So in this type of addressing mode, immediate data is a part of instruction, and it appears in the form of successive bytes or bytes. So here either I can have a 8-bit data or a 16-bit data being specified as a part of instruction. So in order to understand it, let us try to cite an example. So move AX comma 0005H. So here what I have done is I have placed an immediate data 00005H that is being moved to register AX. So here I have specified 16-bit data. Now likewise move DL comma 088. So here I have specified 8-bit data that is moved on to the register DL. So in the above example, 16-bit 005H and 8-bit 08H are immediate data that is initialized to AX and DL respectively. So AX is a 16-bit register, whereas DL is a 8-bit register. So the immediate data, as I've specified, can be of 8-bit or 16-bit in size. Now the next addressing mode that you have is called as direct addressing mode. So direct addressing mode basically specifies that in this case, the effective address of the memory location at which the source data operand is present or is stored is given in the instruction. That is, a 16-bit memory offset or memory address is directly specified as a part of the instruction. So here the effective address is just a 16-bit number written directly in the instruction. So in this addressing mode is called as direct because the displacement of the operand from the segment-based address is specified directly in the instruction. So let us try to understand it with the help of an example. So here move bx comma 1354h. So 1354h is the address of the memory location from where we need to take the value and initialize it to bx. Now likewise move bl comma 0400h. So what it will do, it will initialize bl with the value that is stored in 0400h. So here the square bracket around the values 1354h and 0400h denotes the content of the memory location. So when this particular statement or this particular set of instruction will be executed, this instruction will copy the content of the memory location into the register BX. So this is what direct addressing mode is all about. So direct addressing mode specifies the effective address of the memory location at which the source data operand is present directly in the instruction itself as 16-bit number. Now the next addressing mode that you have is called as register addressing mode. So in case of register addressing mode, the operand is present in the register. So the instruction will specify the name of the register which holds the data to be operated by the instruction. That is, the data is stored in the register and it's referred using the particular register. So this is what happens in case of register addressing mode. So in case of register addressing mode, the operand is present in the register. All the register except the IP may be used in this particular mode. So this is to be remember that all the registers except IP can be used in this particular mode. So here I've specified an example, move CL comma DH. So here the content of the register DH will be moved to CL. So since here DH and CL both are 8-bit registers, so here 8-bit content of the register DH will be moved on to register CL. Now the next addressing mode that you have is register indirect addressing mode. So in register indirect addressing mode, the name of the register which holds the effective address will be specified in the instruction. In contrary to the previous one, here the name of the register that holds the effective address of the operand is specified in the instruction. So here the address of the memory location which contains the data or the operand is determined in indirect way using the offset register. So registers used to hold effective address are any one of the following registers. These are BX, BP, DI, SI. So these four registers can be used in order to hold the effective address of the operand. So in this addressing mode, the offset of the data is either in BX or SI or DI register. So the default segment is either DS or ES. So data segment or the extra segment. So here I've taken a very simple example. Move AX comma in brackets you have BX. So here the effective address of the variable or of the operand is present in BX. So here what I need to do is I need to uh, first determine the base address using this particular effective address or the offset. So base address will be determined by first multiplying ds by with 16 or creating a or appending quadruple zeros at the end, so that we create a 20-bit address. And then memory address is determined by adding the base address with the effective address. So that this we have already learned in the previous classes, the way how 20-bit address is created. So first we multiply by 16 or we append quadruple zeros at the end to a 16-bit base address, and then we add the offset in order to determine the memory address. So here the content of the memory content of the memory location pointed to by BX will be placed into the register AX. So this is the way how register indirect addressing mode basically works. So in case of register indirect addressing mode, the offset or the effective address is specified in the register. So you can have the offset register as BX, BP, DI, and SI, and the default segments will be DS and ES. So here, so the content of the memory location will be pointed to first placed to AL, and then the content of memory location plus 1 will be placed to AH. So this is the way how the registers are initialized. Now the next addressing mode that we have is called as indexed addressing mode. So here the offset of the operand is stored in one of the index registers. Again, I'll repeat it. So here the offset of the operand is stored in one of the index registers. So you have two index registers, SI and DI. So offset of the operand is stored in either SI or DI. Now here DS and ES are the default segments. So extra segment and data segment are the default segments. So SI or DI is used in order to hold an index value for memory location, and an 8-bit and a signed 8-bit or unsigned 16-bit displacement will be specified in the instruction. So this is the way how indirect addressing mode basically works. So here displacement is added to the index value in SI or DI register to obtain the effective address. In case of 8-bit displacement, it is the sign extension to the 16-bit before adding to the base address. So to the base address value. So let us try to understand it with the help of an example. So move AX comma SI plus 0A 2H, right? So here what happens first is, just see here we are moving the content of the address location to the register AX, right? But here the address location is specified as SI plus 0A 2H. Now SI is a 2-byte register, so it's a 16-bit register, so it's holding the offset. Now I am adding a value that is 0A2H, that is A2H, that is an 8-bit number, right? 8-bit number to the content of SI. So first what we'll do is we'll create a extended representation of A2H, that is sign extension of A2H. So sign extension basically means the most significant bit will be extended to the unfilled portion of the bit pattern. So here in case of A2H, so A basically specifies, so A is 10, so it will be 1010, and 2 is 0010, so it will be 10100010. So that is the 8-bit representation for A to H. So in the most significant bit position you have 1. So in case of sign extension of 8-bit to 16-bit, 1 will be copied to the other bit positions. So here if I copy 1 to other bit positions extending from bit position 8 to bit position 15, we'll have FF. So we'll have FFA2. So FFA2 is the sign extension. FFA2 is the sign extension for A2. So sign extension basically means extending the 8-bit data to 16-bit data. So in sign extension, the most significant bit will be copied to all the other higher bit positions. So here E2 will be converted to FFA2H. So now to the content of SI we'll add FFA2H. So that will be the effective address. So this is the way how the index addressing mode will work, right? So here the effective address will be calculated by adding the content of SI, which is 16-bit, and the sign extended 8-bit. So then we'll determine the memory address. So memory address, for that we need to create a shift of the base address. So I'll multiply the content of DS by 16. I'll append 4 zeros at the end of the base address of this segment, so it will become 20-bit address now. So then I will add in order to determine the memory address, I'll add the base address to the effective address. So I'll add base address that is of 20-bit and the effective address that I have calculated by adding the source index and the sign extended 8-bit. So this is the way how the memory address is determined. So now the content of memory address will be placed to the register AX, that is memory address, content of memory address will be placed to AL, then it will be incremented by 1 and the content will be pointed to AH. So this is the way how base index addressing basically works. So in case of base index addressing or index addressing mode, the offset or displacement of the operand is present in either of the index registers, which are SI and DI, and ES and DS are the default segments. Now the next addressing mode that you have is called as register relative addressing mode, right? So in this addressing mode, the data is available at an effective address formed by adding an 8-bit or a 16-bit displacement with the content of any one of the registers, which are BX, BP, SI, DI, and the default segments are either DS and EI. Again, I'll repeat it. So here the data is available at an effective address that is formed by adding 8-bit or 16-bit displacement with the content of any of the 4 registers that are BX, BP, SI, DI. So let us consider an example. So move AX, 50H BX. So again, if I do a sign extension of 50H, so 50 is 0101 quadruple 0. So 0101 for 5 and quadruple 0 for 0. So the most significant bit position has 0. So if I sign extend it, so it will be all zeros in the bit position 8 to 15. So it will be 0050. So 0050 will be a sign extended representation for 50H. So now I need to determine the uh, effective address by adding the content of the register, either of the registers BX, BP, SI, DI with the sign extended value. So here I'm using BX, so it will add the sign extended value to the content of BX. So that is the effective address. Now I need to determine the memory address of the variable. So in order to determine that, we'll first multiply the base address of the segment by 16 in order to create a 20-bit representation. So it's basically appending 4 zeros at the end. So by doing that, we create 20-bit representation of the address, and then to the 20-bit I'll add the effective address formed by adding the content of BX and the sign extended value, that is 0050. So now we'll move the content of the memory location to the register AX, that is content of memory location to AL, and then uh, memory address plus 1 to AH. So this is the way how register relative addressing mode basically works. So in case of register relative addressing mode, the data is available at the effective address formed by adding 8-bit or 16-bit displacement with the content of either of these 4 registers that are BX, BP, SI, and DI. Now the next addressing mode that we have is base index addressing mode. So here the effective address is computed from the sum of the base registers, that is BX or BP, and index registers, that are SI or DI, and the displacement. So this is to be understood in case of base index addressing mode. The effective address of the operand is calculated by adding the content of the base registers BX or BP and the index registers SI or DI and the displacement. So here I have taken up an example: move AX comma BX plus SI plus 0 AH. So now here BX is the base register, SI is the index register, 0 AH is name displacement or displacement value. So now again what I need to do is I need to convert 0AH into 16-bit sign extended value. So if I convert 0AH into 16-bit sign converted value, so it will be 000AH, right? So then we'll add the content of BX, SI and 000AH in order to determine the effective address. So effective address will be BX plus SI plus 000AH. So now in order to determine the address of the memory location, so we need to multiply the base address of the segment by 16 in order to create a 20-bit address. That is to append 4 zeros at the end, or quadruple zeros at the end of the address. So now the memory address will be determined by adding the base address and the effective address. So effective address here is determined by adding the the base register, the index register, and the displacement value. So once the memory address is determined, so the content of memory address is placed into the register AEX. That is, the content of memory address is placed to AL, and then it's incremented of 1, and the content is further placed to AH. So this is the way how base index addressing mode basically works. Now the next addressing mode that we have is called as relative base index addressing mode. So in case of relative base index addressing mode, the effective address is formed by adding 8-bit or 16-bit displacement with the sum of content of any of the base registers BX or BP and any of the index registers, that is SIDI, in the default segment. So this is the way how relative base index addressing mode works. So example, move AX comma 50H BX SI. So this is the way how relative base index addressing basically works. Now the next example, next addressing mode that we have is called as implied addressing mode. Now implied addressing mode basically refers to a situation where the instruction has no operand specified in it. So instruction using this mode have no operand specified in it. So the instruction itself will specify the data to be operated by the instruction. So for example, CLC. So this instruction is capable of clearing the content of the carry flag, right? So implied addressing mode basically refers to a situation where you do not specify any operand with the instruction. Now the next addressing mode that you have is called as port addressing mode. Now, port addressing is used in conjunction with the in and out instruction to access input and output ports. Again, I'll repeat it. Port addressing mode is used in conjunction with in and out instruction in order to access input and output port. Any of the memory addressing modes can be used for port address for memory map ports. So we'll come to memory mapping and IO mapping in the later classes. But for now, just remember that port addressing is used in conjunction with in and out instruction to access input and output port. So we have direct port addressing and we have indirect port addressing. Now, direct port addressing basically refers to a situation where the port number is directly specified in the instruction. So here, in case of direct port addressing, direct addressing of an input port is used in the instruction. So here example, IN AL, 15H. So this stands for input the data from the byte with input port at port at address 15H of the IO address space to register AL. So what it will do, it will place the content or at the input port 15 to the register AL. So this is the way how direct port addressing basically works. So here I'll directly specify the port address in the instruction. Likewise, you have indirect port addressing. So in case of indirect port addressing, the port address is specified in the register. So here input the data from the byte with port whose address is specified by the content of the register DX. So here the port address specified in the register DX. So example, input AL comma DX. So if, for an instance, if DX is equals to 1234H, the content of the port at this IO address are loaded into the register AL. So this is the way how indirect port addressing works. So we can have either direct port addressing or indirect port addressing. In case of direct port addressing, the address is directly specified in the instruction, whereas in case of indirect port addressing, the address is specified in the register. Now the next addressing mode that you have is called as string addressing mode. So a string addressing mode is employed in string operations to operate on string data. Now, the effective address of the source data is stored in SI register, and the effective address of the destination is stored in DI register. So here you need to remember that the effective address of the source is stored in SI, and the effective address of the destination is stored in DI. Segment register for calculating base address of the source data is in DS, and that of the destination is in ES, or the extra segment. So this we have learned in the previous classes as well. In case of string operation, the destination index will be in pointing to the will be used in reference to the extra segment. So segment register for calculating base address of the source data is DS, data segment register, and that of the destination is extra segment. So here move byte. So it's a very simple example that we that have given. So it is self-intuitive. So we will calculate the effective address in the source and the destination, and then we'll move a byte from the source to the destination. So this is the way how string addressing mode is used. So these are the basic 11 addressing modes that we have in 8086. So again, we'll recall. So we've discussed in this particular class, what is an or what are the components of a programming statement. So we've learned that a programming statement has a operand and operand set and the instruction. So 8086 has 11 different ways. So we have learned that 8086 has 11 different ways of addressing the operands. So we have also learned that addressing mode basically specifies the way how uh, the operands are specified in the instruction, specifically the source operand. So we have learned that the way of specifying data to be operated by an instruction is known as addressing mode. That is different ways in which the source operand is denoted in the instruction. So that is what is addressing mode. Then we have learned about different types of statements that may be there in the program. So we have learned that there might be sequential, there might be control transfer based instructions in a programming construct. Then we moved on to different types of addressing modes, where we discussed immediate addressing mode. And then we moved on to direct addressing mode. Then we discussed register addressing mode. Then we moved on to register indirect addressing mode. And then we moved on to indexed addressing mode. Then we discussed register relative addressing mode. Then we discussed based index addressing mode. Then we discussed relative based index addressing mode. Then implied addressing mode, and eventually we discussed port addressing mode and string addressing mode. So these are the 11 basic addressing modes that 8086 microprocessor has. So thank you very much. Have a very good day.